The first few from this tutorial are really just substitutions. Determine the gravitational force of attraction, so it's Fg m1 m2 over r squared, between the Earth, which has a mass, which you substitute in, mass of the student, the distance from the Earth's center is given, and you mustn't forget to square it and substitute in g, and you get your answer. Here we've got a mass of a planet, and we're asked to find the gravitational acceleration on Jupiter. That's different from the gravitational force. Gravitational acceleration is a g, capital G, m over r squared. We're given the mass of Jupiter. We're given the radius of Jupiter. Don't forget to square it. And you then get an answer in meters per second. That's -2, not 2 minus. Here we've got an object. It has a mass of 15 kilograms. And it's placed at the center of a circle. Second object with the same mass is placed anywhere, but it's doubled, and we're going to double that mass, 15 times 2, 30, and we divide the millimeters by 1,000 to get meters, and we square it, and the question is, what is the force? So it's a gravitational force that the mass exerts on the mass. 2-point charges are given to me. They are now placed a certain distance apart, so I can substitute in. Don't forget to times by 10 to the negative 9 to make it coulombs, not nanocoulombs. And then this is an electrostatic force between them, so we're going to have K, Q1, Q2, and K is 9 times 10 to the 9. Substitute in the distance between them. Don't forget to square, and because they have opposite charges, it is a force of attraction. We've got the gravitational acceleration on Earth. The new planet is discovered. It's called Zircon. No, it's discovered in Zircon Galaxy. It has double the mass of Earth and a radius half that of Earth. So what are we going to do? My original, this is like the hard way of doing it. If I double the mass, my force will double. If I halve my radius, my force will go up by a factor of 4. So in total, the new force and the new gravitational acceleration will be 8 times the old one. So it's going to be 8 times 9,8. So let's just go through that. So gravitational acceleration on Earth is equal to 9,8, which is equal to g m over r squared. My gravitational acceleration on, let's say, Zircon is going to be equal to g 2m a half r all squared. That is equal to 2 divided by a quarter g m over r squared. This is 9,8. And when I've got a quarter over here, it becomes 2 times 4 times 9,8. We've got 2 pith balls. They've each got a charge. They touch and are moved apart. So the first thing we have to do is touch them, which means you add them together and divide by 2. And so they've both got negative 2 nanocoulombs on them. And then you substitute the 2 times 10 to the negative 9 for charge 1, 2 times 10 to the negative 9 for charge 2. So you can just square that. They've got a distance between them, 6 millimeters, 6 times 10 to the negative 3 meters. Don't forget to square that, and you put in your K value, and out pops your answer. Here's an electric field around a positive charge. Remember, it radiates outwards, and it's from positive towards negative. What is an electric field? It is a region of space in which an electric charge experiences a force from positive to negative, if you like. And then what is the electric field intensity? A certain distance from a certain charge, K, Q over R squared. Millicoulombs means I divide by 1,000. Centimeters I divide by 100. Don't forget to square, and you get your answer. 3 identical spheres are put on charges, and what is going to happen? So I've got them with those charges originally. First x touches y, and then my new charges are 2, 2, and 0. Now x touches z, so 2 and 0 are divided in 2, so you get 1, 1, and 2, and that's what comes out. And remember, it all happened in nanocoulombs. Add together and divide by 2 whenever charges touch each other. We've got 2 conducting spheres. They're 6 millimeters apart, and they've got those charges on them respectively. What is the force between them? F is equal to K, Q1, Q2 over R squared. Literally just substitute in those values. Don't forget to change the millimeters into meters. Dividing by 1,000. Don't forget to square, and you get your answer. They have got a plus charge and a negative charge, so it's going to be a force of attraction between them. Now we touch them. What charge do they each carry now? I'm going to add those two together. 4 minus 8, I get minus 4, and I divide by 2, and I get negative 2 times 10 to the negative 9 coulombs each. How many electrons were transferred from B to A when they touched? Well, I know that I went from, either way I can do this, I can go from 4 to negative 2, or I could go from 8, what was it, negative 8, sorry, to negative 2. Either way, I'm transferring 6 times 10 to the, and it's negative, obviously I'm becoming more negative, negative 6 times 10 to the negative 19 coulombs. How many electrons are inside that? You're going to have negative 1,6. One electron has a charge of 1,6 times 10 to the negative 19 coulombs, and therefore I find that the number of electrons that has been transferred is 3,75 times 10 to the 10 electrons that are transferred. So you get the charge that is transferred and then divided by the charge on one electron. Now we have got these two neutral balls, and along comes a negatively charged rod. It causes this charge to become negative, this one to become negative as it touches, which then sends some electrons that way, and therefore you have got two negatively charged pith balls and they will repel one another. Explain how the pith ball A acquired that charge. The negative charges were transferred from the ruler to B and from B to the 2A. So those electrons moved along. If 10 units of charge were transferred from the plastic ruler to the pith ball B, what would be the number of charges on pith ball A? Well, if there are 10 that came across there, these guys will divide them in half, and we would land up with 5 on each. If the distance between 2-point charges is given as x, and the electrostatic force is that, what would the electrostatic force be when the distance was reduced? So we don't need to find out, well, let's go with our first F. Our first force is equal to K Q1 Q2 over R squared, and that is equal to X. My new force, sorry, I'm lying, X squared over there. My new force is equal to K, this is 5 times 10 to the negative 4 newtons. Q1, Q2 over a third X, all squared, and therefore I am going to get 1/9 at the bottom. And 1/9 at the bottom really means 9 times K, Q1, Q2 over X squared, and this whole thing is equal to 5 times 10 to the negative 4, and I land up with 9 times 5 to the negative times 10 to the negative 4, 4,5 times 10 to the negative 3 newtons. Two small metal spheres are carrying the following charges. What is the force between them? F is equal to K Q1 Q2 over R squared, 9 times 10 to the 9, 10 times 10 to the negative 6, it's the same, it's microcoulombs. We mustn't forget to square that because there are two charges of that value, and then 100 divided by 1000 is 0,1, and we square that and you land up with 90 newtons. Describe two ways of doubling this force. Well, I could double the charge on one of them. If this was 2, boom, I would get double the force. If this was 2, I would get double the force. If this was a half, whoopsie, I would get a quarter of the force. So I actually need to decrease the radius by a factor of √2. I mean, that sounds a bit weird, but that's what you have to do, because when you square that, you get 1 over 2r squared in the denominator, and therefore that's twice the original force. A charged metal sphere is able to pick up neutral pith ball of 0,4 grams from the laboratory desk. Now, this thing has got a mass of 0,4 grams, which means it has a weight of 0,0004 kilograms times by 9,8. And that turns out to be equal to 3,92 times 10 to the negative 3 newtons. That's holding it downwards. Simultaneously, there would be, if it were to move up, it says here, what is the minimum electrostatic force required to pick it up? So I need to pick it up, I need to get to, the gravitational force has to be exactly equal to the electrostatic force that is going to overcome that. So my electrostatic force minimum requirement is 3,92 times 10 to the negative 3. And if the charge on the metal sphere is given, what is the charge on the induced on the pith ball? So remember, it's a big metal sphere that's attracting this. So I've got two objects with charges, so it's simple. I'm going to say the force is equal to K, Q1, Q2 over R squared, 9 times 10 to the 9. I think this is going to get too big. 3 times 10 to the negative 12. They've told me about that. The charge on the pith ball, I don't know. I do know the distance between them, 0,009, because it's 9 millimeters. Don't forget to square it. I do know the force, I've just worked that out, is 3,92 times 10 to the negative 3. And therefore my charge turns out to be equal to 1,18 times 10 to the negative 5 coulombs. So we've got these two little charge things. They're on threads. They are initially held in those positions. A sequence of events occurs, and a short time later they're like that. If the spheres originally had those charges, they were held like that, remember, because they're opposite charges, what's going to happen? They're going to attract one another. So the first thing that happens is they get attracted. Then they even out their electrons. There's a distribution of electrons. And the next thing is they have the same charge, so they repel one another. So that's the description of what accounts for that movement. Calculate the final sphere on each charge. I take these two together, and then I divide it by 2. So it's negative 11 plus 5 is negative 6. Negative 6 divided by 2 is negative 3 times 10 to the negative 11 coulombs. Determine the number of excess electrons each sphere now carries. I now take that number and divide it by negative 1,6 times 10 to the negative 19, because that is the charge on one electron, and it turns out I get quite a big number. Yep. It's 1,875 times 10 to the power of 8 electrons. And then if the centers of the spheres are now 60 millimeters apart, what is the coulombic force? So it's F is equal to K Q1 Q2 over R squared, 9 times 10 to the 9. I've got the new charge on each one, so it's negative 3 times 10 to the negative 11, negative 3 times 10 to the negative 11, so I can just square that. The distance between them is 60 millimeters. I better convert that to meters and then square it, and my answer turns out to be 2,25 times 10 to the negative 9 newtons. They are now repulsion. And now we have a little polystyrene ball over here, and it's got a thin layer of graphite, and it's in a measuring cylinder, and it's pushed away, and it's got a distance between them. What is the weight of this polystyrene ball? So weight is equal to mass times gravitational acceleration, 0,04 kilograms. 40 grams has to be converted. 9,8, and I get 0,392 newtons down, if you like. Explain why it can be said that the electrostatic force between the two charges is equal to the weight of the ball. Because this is being held stationary, we can say that the downward force of gravity is gravitational acceleration, gravitational force, is exactly equal to the electrostatic force on this guy, keeping it in balance. And by using a calculation, show that the charge on each ball is now 2 microcoulombs. I know the force. F is equal to K Q1 Q2 over R squared, 9 times 10 to the 9. I don't know the charges, but they're identical, so I can square that charge. I do know the distance between them. It's 30 centimeters, so it's 0,3. I divide by 100, and I square it. And I do know the force, 0,392. And my charge turns out to be 1,98 times 10 to the negative 6 coulombs, which really is basically 2 microcoulombs. And finally, these two are a certain distance apart. What is the force between them? It's going to be F is equal to K Q1 Q2 over R squared, 9 times 10 to the 9, 3 times 10 to the negative 9, 5 times 10 to the negative 9, over a distance between them, divide by 100, don't forget to square, and you get 5,4 times 10 to the negative 7 newtons, and because they are opposite charges, that is a force of attraction.